What is the leveling effect? The leveling effect is a property of the solvent which limits the strength of the acids and bases that react within it. So for acids, the strength of the acid is limited or leveled by the basicity of the solvent. In other words, you can't really use acids that are stronger than H3O plus in an acid-base reaction if you choose water as a solvent. The reason is that acid, it's not going to exist with water, because if you use a very, very strong acid, it will react with water, creating H3O plus. So that acid that you want to react in an acid-base reaction, it's going to immediately react with the solvent, and so it's not going to exist anymore. Thus, we could say no acid stronger than H3O plus will exist in water because it will react with water, creating the conjugate acid H3O plus. Now, the same is true for bases. The strength of the base is limited or leveled by the basicity of the solvent. In other words, bases stronger than hydroxide cannot be used in water. If you were to try to put a stronger base than hydroxide in water, that base, it's going to react with water, creating hydroxide, so that base is no longer going to exist in water. Now, let's look at some examples to really see the truthfulness of these statements. Now, let's use HCl. Can we use hydrochloric acid in an acid-base reaction with water as a solvent? Would you say yes or no? In other words, will HCl react with the solvent water? The answer is we shouldn't use HCl in an acid-base reaction if water is a solvent, because HCl will react with water. And the reason being is because HCl is a stronger acid than H3O plus. So if we were to write out the reaction, this is going to be the products. The pKa of water is 15.7. The pKa of HCl is -7, and the pKa of H3O plus is -1.7. So we need to compare these two numbers. Here we can see that hydrochloric acid is a stronger acid than the conjugate acid of water, H3O plus. The lower the pKa, the stronger the acid. So we can't use hydrochloric acid in an acid-base reaction with using water as a solvent because it's going to react with water. Now, in determining the position of equilibrium, it's going to go to the side with the weaker acid. If we compare the acid on the left and the conjugate acid on the right, the side with the higher pKa value, that's where the position of equilibrium is going to lie. So this is going to be a product favor reaction. So we'll have a small arrow to the left, a big arrow to the right. So what this means is that if we put HCl in water, more than 99.9% is going to end up in as H3O plus. Less than 0.1% will be in the HCl form. So we can't use HCl as an acid when water is the solvent because it will react with the solvent. Now, what about using acetic acid? If we were to use acetic acid in an acid-base reaction, can we use water as a solvent? So the conjugate acid will be H3O plus, the conjugate base is the acetate ion. The pKa for acetic acid is about 4.75. And if we compare that to -1.7, we can see that acetic acid is weaker than the conjugate acid H3O plus. So we could use acetic acid in water if water is a solvent, because for the most part it doesn't really react with water. This is a reactant favored reaction. The position of equilibrium lies to the left towards acetic acid. So because acetic acid is weaker than H3O plus, for the most part it doesn't react with water. And so we can use acetic acid in an acid-base reaction with water as a solvent. So the leveling effect let me say that again. The leveling effect limits the strength of the acid that we could use when water is a solvent. In other words, we can't use acids that have a pKa that's lower than negative 1.7 or significantly lower than 1.7. If it's like negative 1.8, that's close enough. You're going to have a 50-50 reaction. You could use that. But using an acid with a pKa that's like negative 4 or less, it's not going to be a good choice if water is a solvent because it will react with the solvent. Now let's look at bases. Which base can we use in an acid-base reaction with water being a solvent? Would you say fluoride or terbutoxide? When fluoride reacts with water, it will create HF and hydroxide. When terbutoxide reacts with water, it will create terbutanol and hydroxide. The pKa for HF is 3.2. For water, it's 15.7. And for terbutanol, it's about 18. So the first reaction, would you say it's product favored or reactant favored? Well, this is the weaker acid because it has a higher pKa, so this is going to be reactant favored. This one is the weaker acid. It has a higher pKa, so this is going to be product favored. So the answer is we could use fluoride in an acid-base reaction with water as a solvent because this is a reactant favored reaction, which means it's not going to react much with water. Using terbutoxide is really not a good idea because the majority of it will react with water. Now the pKa difference is about 2, so we're dealing with a factor of almost 100. So about 1% or less than 1% will be in this form, but greater than 0.1%. More than 99% will be in this form. So if we were to use terbutoxide with water as a solvent, much of it will react with the solvent. However, if you're okay with this 1% reacting with the target base, then that might be enough to work, but for all practical purposes, 1% may not be enough. So this wouldn't be a good choice to use if water is a solvent. So notice that the strength of the base that we use is limited by the strength of hydroxide. So let's see if we can put a visual illustration to this. Let's put water in the middle. Let's put H3O plus here. It's more acidic than water. And let's put hydroxide to the left since it's more basic than water. Now HCl is stronger than H3O plus, and the same is true for H2SO4. So I'm going to put that in the right. Now acetic acid is more acidic than water, and H2S is also more acidic than water, but less acidic than H3O plus. The sulfide ion is more basic than water, but not stronger than hydroxide. And the same is true for the acetate ion. Terbutoxide is a stronger base than hydroxide, and this is the acetylide ion, the conjugate base of acetylene, which is an alkyne. That's a stronger base than terbutoxide. So based on the leveling effect, we can't use any acids stronger than H3O plus when water is a solvent. So we can't use HCl and H2SO4. If we do, they're not going to exist in water because they will react with water. And we can't use bases that are stronger than hydroxide. So everything outside of that range on the left or on the right can't be used. So we could use acids and bases in this range. We can use acids that are weaker than H2O plus, and we could use bases that are weaker than hydroxide. Those will be free to participate in acid-base reactions when water is a solvent. So that's the basic idea behind the leveling effect. If you choose water as a solvent, no acid stronger than H2O plus will exist in that solution, and no base stronger than hydroxide will exist in that solution for all practical purposes. I mean, there's going to be a level of equilibrium, 1%, 99%, but for all practical purposes, if you were to use a stronger acid, that stronger acid is going to be, at least most of it, will be converted into H2O plus. If you were to use a stronger base than hydroxide, most of those bases will be converted to hydroxide. So let's put a practical problem to this. Let's say we have 2,4-pentadione, a beta diketone. And here is the acidic hydrogen, also known as an alpha hydrogen. When it's between two carbonyl groups, the PKA is around 9. Now, the solvent is water. So this is going to be the acid. We want to remove that proton, with water being the solvent. Once we remove the proton, we're going to get a conjugate base that is stabilized by resonance among the two oxygen atoms. That negative charge can be placed on the two oxygen atoms, and that's why the pKa of this proton is fairly low for a CH proton. Now, which base should we use? I'm going to give you 3 choices. Should we use phenoxide? Should we use acetate? Or should we use the amide ion, NH2-? Now, let's think about what we need. We need a base that's strong enough to deprotonate this hydrogen, but not strong enough to react with the solvent water. Which of these 3 bases will do the job? The pKa for water is 15.7. So let's look at the pKa's of the conjugate acids. The conjugate acid of phenoxide is phenol. The conjugate acid of acetate is acetic acid. And the conjugate acid of the amide ion is ammonia. Phenol has a pKa of around 10, acetic acid 4.75, and ammonia 36. So with this information, which base is strong enough to deprotonate the acidic hydrogen, but not strong enough to react with water? What answer would you pick? So first, let's find out which bases are strong enough to remove that hydrogen. What we need to do is compare the pKa of the acid and the conjugate acid. So looking at these two, phenol has a higher pKa. That means it's a weaker conjugate acid. So this is going to be a product favored reaction. This means that phenoxide is strong enough to remove this hydrogen because we have a stronger acid on the left and we're forming a weaker acid on the right. So this is a product favored reaction. So phenoxide is strong enough to deprotonate this hydrogen. Now what about acetate? If we compare the pKa of the acid and the pKa of the conjugate acid, this is less than 9. So this is not going to be strong enough because this is a stronger acid, this is a weaker acid. The position of equilibrium is towards the weaker acid. So this is a reactant favored reaction. So because it's reactant favored, that means that acetate will not be strong enough to remove this hydrogen. So acetate can exist in water, but it's just not strong enough to take off that hydrogen. What about amide? If we compare these two, the pKa of NH3 is higher than the acid on the left, so this is going to be a product favored reaction. We have a weaker acid here, a stronger acid here, and the reaction is going to favor the formation of stable products or weaker products. So amide is strong enough to deprotonate this hydrogen. Now, we need to find out which base is not strong enough to deprotonate water. So now we need to react them with water. They're going to form the same conjugate acids, but also the conjugate base hydroxide. So this time we're comparing 15.7 with these values. So if we were to mix this with water, will they react? Comparing the pKa of water and phenol, this is bigger, so this is the weaker acid, this is the stronger acid. The position of equilibrium will favor the weaker acid, so this is reactant favored, which means that it's not going to react with water. So that's good. Now, if we were to react this with water, we would compare these two pKa's. This is the weaker acid, this is the stronger acid. The position of equilibrium will favor the weaker acid, so it's product favored, which means that this will react with the solvent. So because it reacts with the solvent, we don't want to use that. If we were to take amide, mix it with water and its diketone, water being a solvent is likely going to be much more abundant than its diketone, this beta diketone. As a result, amide is going to react with water long before it reacts with this. Maybe a small amount of this will get reacted, but the majority of the amide is going to be eliminated by the water. As soon as it hits that water, it's gone. So more than 99.9999999% of this is going to be turned into ammonia. So for all practical purposes, this is really not going to get a chance to react with the target acid, because it's going to react with the solvent immediately once you dissolve it in water. So the appropriate base to use in this example has to have a pKa, that is the conjugate acid has to have a pKa that is greater than the target acid but less than the solvent. So we need a base whose conjugate acid has a pKa between 9 and 15.7, ideally speaking. If it's around 8 or 17, it could still work. So give or take, 1 pKa unit. Because if you differ by 1 pKa unit, I mean, the ratio of acid and base is like 10. So it could be like 90%, 10%. Close to that. But for all practical purposes, you want to choose a base whose conjugate acid has a pKa that's higher than the target acid, but less than the solvent. So phenoxide fits this well. The conjugate acid of phenoxide has a pKa of 10, which is between the pKa of the target acid and the pKa of the solvent. So that's how we could determine the appropriate base to use that's strong enough to react with the target acid, but not strong enough to react with water. So amide, we can't use that because amide is a stronger base than hydroxide. So that's not going to work. But this is an easier way to identify the appropriate base. It's by knowing the pKa range of the conjugate acid of that base that you can use. So that's basically it for this video. Hopefully it gave you a good introduction into the idea of the leveling effect. So the basic idea behind the leveling effect is that we're limited in the choice of our acids and bases that we can use in a solvent. We can't use an acid that's stronger than the conjugate acid of the solvent, and we can't use a base that's stronger than the conjugate base of the solvent. Now, for those of you who want to access my extended organic chemistry videos, you can access it at my Patreon membership program at patreon.com/mathsciencetutor, or in my YouTube membership program, which you can join in the video below. Now, if we click on this organic chemistry post, it'll show you all my full-length organic chemistry videos. So I have this video on pKa values for those of you who are studying acids and bases. For those of you who are just studying organic chemistry, this basic introduction video will really help you get started. And I have some other videos as well: hybridization, resonance structures. The free version of this video is about 20 minutes long on YouTube, but the full-length version is about an hour long. Acids and bases, functional groups, Newton projections. The worksheet contains all of the problems in the full-length video. Some of you have asked for worksheets. You prefer to work through the problems that way instead of watching a long video. So I have it for not all of my videos, but some of them. So we have chair confirmations. Now, for my organic chemistry exam 1 video, you may have to type it in the search box to get it. Or if you look at the description section of the referring video, it'll take you directly to that link. But here is the worksheet. Now, if you want to watch a 7-hour video, you can do it that way, but if you prefer to print out the worksheet and work through the problems that way, you could do that as well. By the way, post a comment in below this video. I want to know what your thoughts are. Do you prefer to watch the 7-hour video, or do you prefer to study for the exam by getting a printout of the worksheet and working through the problems while you're in school? Let me know in the comment section below. Now, I have other videos: stereochemistry, specific rotation, SN1, SN2 reactions. There's a practice test on that, 77 practice problems. So here's the video with the practice test, but I haven't done the worksheet yet. We got alkene reactions, alkyne reactions, alcohol reactions, radical reactions, and then my organic chemistry 1 final exam review video. So the video is actually finished, but the worksheet is coming soon. So let me know, for those of you who are actually interested in getting these worksheets, do you prefer to watch a 6-hour final exam review video, or do you prefer to have a printout of the 100 practice problems and work through it at school? Let me know in the comment section below.